morning. So today we will discuss about buffer and NOT gates. So in previous class we discussed different types of gates, that is AND and OR. So in previous class we discussed about AND, OR, NOR, XNOR, XOR. These are all the basic gates, that is a class 1. So second class is we name it as buffer and NOT gates. So the specialty is buffer and NOT gates have one input, right? That is one scalar input or one or more scalar outputs. That is a single input and as well as one or more outputs. Then again here the last terminal of the instantiation is input, the remaining are outputs. Because of clearly mentioned only a one input, then there are one or more outputs. Okay, then first we write the symbol of the buffer and NOT gates, then we write the truth table, then we write the instantiation of buffer and NOT gates. First we have to write the symbol of buffer and NOT gates. So this is the symbol of a buffer one. Then next we write the in and out. So this is the symbol of a inverter gate, that is inverter, and also we called as name it as NOT gate. So in buffer and NOT gates there are two primitive gates, that is primitive symbols. The one is we name it as buff, that is buffer, then other one is NOT. Next we write a truth table of a buffer and NOT gates, that is truth table can be written as here. Let us assume one input and one output. So input can be named as in, then out. So here there are four combination, that is there are four values applied here, that is 0, 1, then don't care, then I impedance. That is what is similar to a previous AND and OR gate. So first let us assume the input is 0. So when the input is 0, then the output of the buffer is 0 only. When the input is 1, then output is 1. So that indicates whatever input you applied in terms of 0 and 1, the output is follows the input. Next we have to apply, suppose it's don't care, either 0 or 1, and that time output is don't care only. Then suppose we have to apply the I impedance, that is SZ, and that time it produces a don't care, that is either 0 or 1. So this is the a truth table for a buffer. Next we have to write the truth table for inverter. Then in, out. So here first we have to apply the 0, then output is 1, then we applied 1, then output is 0. That indicates whatever input you applied, the output is complement of that input. That is input is 0, then that time output is 1. Next input is 1 and that time output is 0. Then suppose you applied don't care, and that time the output should be don't care only. Either you applied 1 or 0, but there is no changes the in and out. That is we applied don't care, then output should be don't care only. Then suppose you applied Z, then it produces X. This is the a truth table for a buffer and inverter. So based on this symbols we have to write the instances of buffer and NOT gate. So here these are all some examples with respect to instances. So in first example, buffer is is predefined word, or we name it as that word is primitive. So buff, then B1. So we know the rules and regulations of that gate level description. So in gate level description first we have to write the output. So that's why we mentioned out, then comma in, that is the input. So here also first you have to mention a predefined word. The predefined word, or also we name it as a primitive gate. That is primitive gate is the name of the primitive is B2. Then first you have to mention the out, then in. Suppose next it's more than one output, then on that time this can be modified for buffer, then B3, then there are, we have to assume two outputs, that we name it as out 1, then out 2, then in. So here there are two outputs, then one input. So in definition he clearly mentioned one or more scalar outputs, then only one input. So suppose next we just modify this equation, a buffer out 1, out 2, then in. This indicates there is no name mentioned here. In earlier one you have to mention the what name, that is B3, but here there is no name required here. Okay, so that is, you directly write buffer out 1, out 2 and in. So these are all the what regarding buffer and NOT gates. So next topic, buff if and not if. So in previously we discussed buffer and inverter. So here we discuss about buff if and not if. So what's the difference compared to a previous one? So here we have to assume a control signal here. We have to apply a control signals. That is the first one. Then when you apply that control signal, obviously there is a lot of variation with respect to output. Then here there are four primitives are available here. That primitives can be named as buff if 1, then buff if 0, then not if 1, then not if 0. So these are all the four primitives with respect to buff if and not if. So here, so 0 and 1 indicates low and high. So after this, here the speciality of this buff if and not if is when the output, that is the gate can propagate only the control signal is asserted. Then otherwise the value of the output of this gate is Z if what the control signal is deserted. It means the output is enabled only on what control signal is enabled. Then when the control signal is disabled, then output is produces then high impedance. Okay, so that is the specialty here. So these are all the what a symbols with respect to buff if and not if. Here the first one is buff if 1. So why we call it as it's 1? Because the control signal is logic 1. The control signal is logic 1, and that time the output is some values either 0 or 1. This one is what a control 1. Again control applied here, then we name it as buff if 0. Why buff if 0? Because the control signal is what? Complement here. We have to apply the control signal is complement, that is 0, and that time only the output is what? Propagate. So here not if 1 and not if 0. So why we call it as not if 1? Because the control signal, okay, the control signal, you have to apply logic 1 and that time output is propagate. Here the control signal is logic 0 and that time output is propagate here. This is the truth table regarding all the four, that is buff if 1, buff if 0, then not if 1 and not if 0. So let us go one by one. Here the first one we have to assume buff if 1, then here there are two inputs, then in is the one input, another one is control is the what? Another one. So here when you applied input is equal to 0, whatever input you applied, but it depends on the changes with respect to control signal. Okay, that is very important here. So when you applied input is equal to 0, then control signal is disabled. That is control signal is 0 for what? It regarding a first one, that is buff if 1. When input is equal to 0, then control is equal to 0, then it produces Z, that is high impedance at the output side. Then input is equal to 1, and that time control signal is equal to 1. So it indicates the control signal is enabled, and that time when input is 0, then control signal is 1, then output follows the input, that is output is equal to 0. Then when you applied input is equal to 1, then output is equal to 1. So we know the meaning of buffer, that is whatever input you applied, then output is follows the what? A input. Then suppose you applied don't care, and that time it produces don't care only. Suppose you applied high impedance value, and that time it produces a don't care. So look at a speciality here. Then when you applied then high impedance and as well as don't care. So when you applied input is equal to 0, then it produces low. Then when you applied input is equal to 1, then it produces high. Then what's the difference between 0 and low than 1 and I? So that is the question here. So here the meaning of L, it's little bit of different compared to 0. The L, it may be either 0 or it may be a I impedance. Okay, it produces 0 or I impedance. So H, it means it produces 1 or I impedance. Okay, that is the what meaning of L and H. It produces clearly 0 and 1. But when you applied control signal is X and Z, and that time L, that is low as well as high. So it means the L means the value is 0 or I impedance, the H means the value is 1 or I impedance. Okay, so that is the specialty here. Then similarly buff if not, so its control signal is it's at 0 here. Okay, when you applied 0 and that time it's enabled. So look at the truth table here. When you applied 0 here, the control signal is 0, and that time when you applied input is equal to 0, output is 0, input is equal to 1, output is 1. When you applied don't care term, on that time don't care. When you applied an impedance, then on that time it produces a don't care. So look at the difference here. When you applied control signal is equal to 1. So what's the changes here? When you applied control signal is equal to 1, and that time it's deserted. Okay, then output is what? Not propagate here. So on that time it produces what? I impedance 1. So remaining the X and Z values are similar to what? A buff if 1. Then move on to next one, that is not if 1. So not if 1, it's exactly opposite of what? A buff if 1. When you applied 0 here and that time the control signal is enabled, then it produces 1. Then when you applied 1 and that time output is 0. Here is also some modification here. When you applied input is equal to 0 and that time the control signal is X or Z, and that time it produces H, that is exactly opposite of what? A buffer. Okay, then you applied 1 at input is equal to 1, then it control signal X or Z, and that time it produces what? A L here, that is low. Then not if not exactly is opposite of what? A buff if not here. After this truth table, next we have to write some instances here. It's very important thing. Here how to instances, that is the question here. The first one, instantiation of buffer and not gate. So buff if 1 is a predefined word. It's a predefined word. Buff if 1, that is B1. Okay, name of the what? Primitive is B1. Then first we have to write the output, that is out. Then next we have to write inputs. That is what are the inputs here? The first one is in, then second one is control. So it's similarly next we have to write buff if not. So buff if not B2, then out, then in and control. Here out is output, in and control is the input here. Okay, so next similarly for not if 1 and not if 0. Next move on to some examples with respect to gate level description. So here let us assume a gate level multiplexer. So that is, we know that multiplexer meaning, that is it indicates a many into 1. That means many inputs, only one output. So here multiplexer is specially designed for a digital logic design. When you write the gate level multiplexer or simply multiplexer using gate level description, and that time first we have to write a block diagram. Next, based on that block diagram we have to write a truth table. Based on the truth table we have to design a circuit, that is a logic circuit. Based on that logic circuit we have to write a gate level description. So without what logic circuit we can't write a gate level description. So the name indicates it depends on that circuit gates. So first here let us assume 4:1 multiplexer. The 4:1 multiplexer, there are what? A 4 inputs, then 1 output, then 4 inputs in the sense 2 power n, that is n number of lines. 2 power 2 is what? A 4 inputs, then n select lines, that is n is equal to 2 here, there are 2 select lines. So first we have to write a block diagram. So this is the block diagram for 4:1 mux, or we call as multiplexer. So I0, I1, I2 and I3 are the inputs, then S1 and S0 are the select lines, then outputs. So based on this block diagram, we have to write a truth table. So here for truth table, S1 select line, that is S0, one more select line, then you would write out, that is output. Then first here there are two select lines, it means there are four combinations, that is four combinations here, that is 2 power 2, there are four combinations. The first we have to assume start with 0 0. When you applied 0 0, then which one is selected? That is I0 is selected here. Then when you applied 0 1, then I1 is selected. When you applied 1 0, then I2 is selected. Last one 1 1, I3 is selected. These are all the combinations regarding a 4:1 mux you already studied in a third semester as well as in basic electronics. Okay, in third semester, that is digital system design. So next, move on to equations here, because when you write the circuit on that time, equation is what? Very important here. So only here the out is equal to first combination you have to write, that is what? First I0. So I0 is selection is based on what? S1 and S0, that is both are what? 0 0. That's why we write S1 bar, then S0 bar. So when you select second line, that is I1, on that time, so here S1 is complement 1, then S0. Then next I3 is selected, I2 is selected, and that time S1 is equal to 1, then S0 is what? A complement 1. Then last one I3 is selected, and that time then S1 and S0. Okay, so based on this equation we have to write a logic circuit. So what are all the requirements of this 4:1 mux? Here we are using a basic gates. Okay, here we are using a basic gates, that is AND, OR and inverter. S0 and S1 both are complement, right? So on that time for S0 one NOT gate is required, then S1 another NOT gate is required. So there are two inverter or NOT gate is required here. Then how many AND gate is required? There are four combinations, right? So there are four combinations. There are four 3 input AND gate is required here. There are four 3 input AND gates. Then here plus, that is we add what? All four equations. So that's why here 4 input OR gate is required. Okay. So what are the requirements? 2 NOT gates, then 4 AND gates, then 1 OR gate is required. A design 4:1 mux. So after logic circuit, based on that logic circuit, we have to write a code for this a gate level description. So based on that equation, we have to design a logic circuit for 4:1 mux. So here there are two inverters is required, right? So that can be written as that is S1 and S0. So complement of S1, here we can't write S1 complement. So that's why we named as S1N, then here we named as S0N. Okay, then what is the first equation here? That is first term I0, S1 complement and S0 complement. Then here S0 complement, then S1 complement, then one more, that is I0. Then it produces one output. So that can be named it as, you have to assume it's an Y0. So next one I1, S1 complement and S0. So here So first S0, right? So here this is the what? S0. Then S1 complement. This is the S1 complement. I1. So this output can be assumed Y1. So next one, I2 selection. So for I2 selection, S0 complement. Here this is the S0 complement. Then S1. S1, then input I3. So this can be named as Y2. Then next one, last one, that is last select line, that is last input. Then here S1 and S0. S1, S0, then I1, I2, I3, then it produces Y3. Okay, again it is not over. So we need to connect all AND gates to what? OR gate. So that is, we have to assume a 4 input OR gate here. Out. So this is the logic circuit regarding what? A 4:1 mux. So based on this 4:1 mux, we have to write a gate level description programming, that is using a Verilog. Let us assume what are the requirements here for write the code. So requirement is S1N, then S01. So we call it as nets, or we name it as intermediate signals. And also there are more intermediate signals here, that is name it nets or intermediate signal, that is Y0, Y1, Y2 and Y3. So here totally there are 6 intermediate signals. So that is S1N for S1, S0N for S0, then output of the AND gates, that is Y0, Y1, Y2 and Y3. So all are connected together for OR gate, then it becomes an output. So next we have to write this. So first we already discussed, the first is always start with module. So name of the module is, let us assume mux 4:1. So inside the what? Module terminals, we have to write what inputs and outputs. So what are the inputs here? That is I0, I1, I2, I3, then S1, S0, then finally out. So these are all module terminals. So after the module terminals, we have to declare a module terminals, that is what are all the inputs and outputs. So input can be declared as input I0, then I1, I2 and I3. Then one more input is there, it can be written as input S1 and S0. Then after this, what are all the outputs here? So output can be declared as output out. Okay, next once you declare the inputs and outputs, next we have to declare a intermediate signals. So that can be named as a wire. So wire can be written as S1N, then S0N, Y0, Y1, Y2 and Y3. These are all the intermediate signal with respect to this circuit. Then after this we have instances, that is instantiation of one by one. First we have to instantiate a inverter. So this can be written as predefined word or primitive for the inverter. The first one you name it as N1. So what is the output here? Obviously for now N1, S1N is the output, then S1 is the input. So only one input, then one output. First we have to write the output, that is S1n, comma S1 is the input. Next primitive gate, that is not again, that is name it as N2. Then what is the output? S0 here, S0 n, then input is S0, S0 n, then S0. So this is the primitive gates. It belongs to a inverter. Next, there are 4 AND gates here. So that can be written as AND is the predefined word. So you name it as A1, in bracket you write. So what is the inputs and outputs? So Y0 is the output. Then what are the inputs? That is S1n, then S0n, then I0. That is the and A1. Then suppose you write one more, that is second one. Here and A2, that is output is Y1. So where it is connected? That is here S1n, that is S1n, then S0, then it one more input, that is I1. So next one, and A3. So that can be written as Y2, then Y2 is the output. Then what is the input? That is S0n, then S1, then I2. Next, for last one, and A4. For AND A4, Y3 is the output. Then what are the inputs? So S0, then S1. So S0 and S1, then one more input I3. Right? So these are instances regarding a AND gate. So one more gate is there, that is last one OR gate. So we have to write the instances for OR gate. So OR gate instances can be written as OR is a predefined word, then you name it as O1. Then what are the inputs and outputs? Obviously first we have to write output, that is out, then inputs Y0, Y1, Y2, then Y3. Okay, then program is end module. Again I repeat this. First is always start with a module, right? That is module. The name of the module is MUX 421. That is the name of the module. Then after this we have to write a module terminals. So module terminals means what all the terminals are available here. So there are 7 terminals, that is 4 inputs, then 2 select lines, then 1 output. 4 inputs I0, I1, I2, I3, 2 select lines S1 and S0, then out. Then after this we have to declare ports, that is what are the input ports and output ports are available. Input ports are I0, I1, I2 and I3. Again select line is also inputs, that is input S1 and S0. Then what are the outputs are available? Output, there are only one output, output out. Then next we have to write some intermediate signals. We have to assume some intermediate signals. So what are the intermediate signal here? So here when you observe the truth table, there is a word complement. On that time we should assume a intermediate signal. So S1 is complement, we have to assume S1n, then S0 complement, we have to assume S0n. So these are the what 2 intermediate signal. Again the output of AND gate is connected to OR gate. Again we need some intermediate signals, that is Y0, Y1, Y2 and Y3. These are all the intermediate signals. Okay, there are 4 intermediate signal that can be named as wire in Verilog HDL. That is S1n, S0n, Y0, Y1, Y2 and Y3. So next we have to instances. Okay, instantiation each and every gate. How many gates here? 2 inverters or 2 NOT gates, then 4 AND gates. So first we have to instantiation of what inverter here, that is not N1 is the name of the first inverter, that is S1N is the output. First we have to write the output, next input, that is S1N and comma S1. So next instance this is a second one, so that is not N2 is the name of the second one, then S0N and S0. So next we have to write a remaining one, so AND gates. So AND A1 Y0 is the output, inputs is S1N S0N, then I0, then for AND A2 Y1 is the output, S1N S0 comma I1, then AND A3 Y2 S0N S1 and I2, for AND A4 Y3 S0 S1 I3, then for finally OR together, that is OR O1 out, there are 4 inputs Y0, Y1, Y2 and Y3, then AND module. Any confusions regarding this gate instantiation, you simply mention the what name of the gate directly here. So first one is N1, then here N2, then for AND you name it as A1, then A2, A3, then A4, for here O1. Then you can easily what write the what a gate instantiation, that is a gate level description. So this is the what a gate level description for a 4. Let us continue with respect to a stimulus block. So here stimulus block is always start with module and name of the module. You can name it as any name. Here better to name it, name of the module is stimulus. So don't declare the ports here, that is belongs to what design block only. So you simply name it as module stimulus. Then after this you have to mention a resistors and wires. So here resistor, there are 4 resistors here, IN0, then IN1, IN2 and IN3 is to 1 multiplex. 4 inputs and S0 and S1. So there are totally 6 resistors here. So IN0, IN1, IN2, IN3 are the inputs. So here why it acts as a resistor, we already discussed with respect to module 1. Why resistor? Because here we have to store the data, we have to apply some data. So test means either if it is correct or wrong. So that's why we have to store some data. So here resistor, the name indicates we have to store the data here. So that's why here mentioned resistor IN0, IN1, IN2 and IN3 and also S0 and S1. So based on these select lines, the output is what? Select one. Okay, so that's why you have to mention the resistor. So after the resistor declaration, next we have to mention wire, output. Okay, so only one output at the multiplexer, so that is wire outputs. So wire output acts as a what? Here signal. So with respect to what? A stimulus block. Okay, that is a test bench code. So once you declare the outputs, that is output, and as well as once you declare the a resistor, so next you have to apply the data. So it always start the word initial. So we are using a begin. Why we are using a begin? Because here we have to apply totally 5 to 6 combinations, right? Because S0 is equal to 0, then S0 is equal to S1 is equal to 0. So totally 4 combination, and also we have to initialize the data. So next we have to initialize the data. So let us assume IN0 is equal to 1, then IN1 is equal to 0, then IN2 is equal to 1, then IN3 is equal to 0. So that is IN0 is equal to 1, then it is 0, then 1, 0. It's just an assumption. You can assume any other data. Okay, that's the initialization of the A input. After initialization of the input, next we have to choose one by one. First we choose a first one, that is, what is the first input here? That is IN naught. So here after choose the what? IN naught. Next we go to IN1, IN2 and IN3 and IN4. So what's the data requirement of choose the IN naught here? So obviously when S1 is equal to 0 and S0 is equal to 0, and that time IN naught is selected, right? So that's why here first you have to select S1 is equal to 0, then S0 is equal to 0. So on that time I0 is selected. So after you select the I0, that is S1 is equal to 0 and S0 is equal to 0, you have to display the data. So how to display the data? That is we already discussed in previous module. That is a dollar display we are using in displaying the what? A result. So here dollar display. So after the dollar display, first S1 is equal to, so what type of data you have to apply here? So that is S1 is equal to 0 and S0 is equal to 0. So 0 in the sense here we have to apply binary data. So that's why S1 is equal to, you have to mention percentage binary. So it indicates percentage binary, it indicates display the result in the form of a binary data. So once your S1 is completed, next you should apply the what? S1 after S0, that is you have to mention percentage B. Again it should be a binary data. So after this result, that is output is equal to, again the output is displayed in terms of a binary. Okay, that is it should be a binary data. Then after this it should be end line, that is new line. So end, then after the end you have to display the S1, then S0, then output. So this is the what? A choose IN0. Next we have to choose next one, that is IN1. So it can be written as S1 is equal to 0, then S0 is equal to 1. So it indicates display, dollar display, then S1 is equal to percentage B, then S0 is equal to percentage B, then output B slash N, then S1, S0, output. Then after again you have to display two more data, that is IN0 and IN1. So next we have to display S0 is equal to 0, sorry S0 is S1 is equal to 1, S0 is equal to 0. Then obviously it displays a next one IN0, IN2, IN1. Next here it displays a IN2. Then again dollar display, so after this you have to display one more data, that is S0 is equal to 1, S1 is equal to 1. You have to display the result. So you have to mention, then after this, then there is a begin, you should end, then end module. Okay, so here I skip that one, that is S1 is equal to 1, S0 is equal to 1. Okay, next you have to write S1 is equal to 1, S0 is equal to 1. And after this there is a begin, it should be end, then end module. So this is a stimulus program for a 4:1 multiplexer. Once you mention the what? Register, then wire, then here one thing is missing here. Okay, before you initialize, first you should instantiate the data here. So that instantiation is done with, that is it should be same name. We already mentioned mux to 1, that is the name of the a design block. So name of the instantiation you have to assume mux. So what are the inputs and outputs you have to clearly mention. So during instantiation, first you have to mention the output, that is the process. Next you have to mention the inputs, that is IN0, then IN1, then IN2, IN3, then S1 and S0. Okay, so this is the what a process of a instantiation. So again I repeat this, for 4:1 mux using a stimulus or using a test bench. So once a design block is completed, okay, so up to previous class the design block is completed one. Okay, we need to test the data. So that can be done by a stimulus, or we simply name it as a test bench code. So module, name of this module is stimulus, or you can write test bench, or you can write mux. Okay, so here stimulus is not a predefined word. Then after this, here register IN0, IN1, IN2, IN3 and also register S0 and S1. So why here register? Because we have to force some data, we have to apply some data. Okay, so that's why we store some data here. So that can be done by a register. So we know the meaning of register. So using that register, you have to store the data. So next, wire output. Obviously here output acts as a what? A wire during test bench. So after this, we need to what? Instantiate the data. So that can be done by mux 4:1, right? Mux 4:1 here. So here the name should be what? A similar. Okay, it's similar to what? A design block. Okay, here this line indicates design block is what? It's instantiate with the a stimulus block. Design block instantiate with the stimulus block. So in during stimulus block, first you have to mention the output, that is output IN0, IN1, IN2, IN3 and S1 and S0. Then after this you have to initialize the data. The process is start here, initial, begin. Why we are using begin? Because we have to apply 2 or more datas. Okay, that's why we are using begin. First you initialize the all the inputs, that is IN0 is equal to 1, IN1 is equal to 0, then IN2 is equal to 1, then IN3 is equal to 0. Then after initialize the data, next we have to apply the what? A selected inputs. Okay, that is select lines. So here first we choose IN0, that is when IN0 S1 is equal to 0 and S0 is equal to 0, and that time the output select the first input, that is IN0. So here next we need to display the data, that is we are using $display, that is $display S1 is equal to %B. So obviously here we choose the what? In the form of binary. So that's why we choose here %B. That indicates you have to display the data in terms of binary. If it is decimal, you have to mention %D. If it is hexadecimal, mention %H. If it is octal, and that time you mention %O. Then after this, S0 is equal to again in the form of binary, then output is in the form of binary. Then after this one binary data, you have to display the what? Result, that is S1, S0 output. So similarly, whatever choose here, S1 is equal to 0 and S0 is equal to 0, same thing you have to apply here. Next S1 is equal to 0, S0 is equal to 1, then S1 is equal to 1, then S1 is equal to 0. Next we have to apply S1 is equal to 1, S0 is equal to 1. Then after this, there is a begin. It should be what? End. That is end, then end module. The module should be end. This is the what? A 4:1 mux using, that is 4:1 mux using a stimulus block.